You press a key, a spring compresses, a tiny metal contact closes, and the letter A appears on your screen instantly. But a computer doesn't understand letters or intent. We are qualitative, emotional creatures, trying to communicate with a physical rock that we've tricked into thinking by shooting electricity through it. The machine only understands whether a circuit is open or closed. In the early days of computing, the gap between human intent and machine logic was a physical one. You had to manually wire connections across massive cabinets just to run a basic calculation. Today, that gap is bridged by the distinction between data and information. Data is what the machine processes, raw, unorganized facts and binary signals. Information is the result, data that has been organized, contextualized, and rendered into a format we can use. Turning a physical keystroke into useful information requires an intricate assembly line. Hardware and software must work in perfect synchronization to translate a human command into a machine action. Every response to a key press is a microscopic logistical operation, coordinating millions of discrete steps in a fraction of a second. The journey begins at the interface. A voltage spike travels from your keyboard, down a wire, and into the internal architecture of the system. That signal hits the compiler, the ultimate translator. It takes human-readable commands and shatters them into the exact sequence of ones and zeros the machine requires. Now the system is flooded with machine code. To prevent a bottleneck, the operating system acts as the internal traffic cop, directing where every piece of data needs to go. This table outlines the two main categories of software the operating system manages: system software and application software. While users choose which applications to run, the operating system prioritizes system software. As this row shows, it is compulsory. The hardware cannot function without it. Once the operating system establishes priority, it moves the required data out of slow, long-term storage and loads it into the high-speed staging ground of random access memory, or RAM. This software logic gives the physical components their purpose. Without these instructions, the motherboard and CPU remain inert, a dormant network of silicon and circuits waiting for a signal that never arrives. Once the data is staged in RAM, it enters the physical hardware layer. Here, information must traverse the physical distances across the motherboard. It travels along the bus system, specialized conductive highways etched into the board that rush data from memory straight to the central processing unit. Inside the CPU, the system executes the fetch, decode, execute cycle. The control unit pulls data off the bus and locks it into ultra-fast staging areas called registers. Then the arithmetic logic unit takes over. Deep inside the silicon, the ALU performs the final mathematical calculations and logical comparisons at a microscopic level. With billions of electrical signals firing simultaneously across different components, the system faces a threat of internal chaos. If components send data at conflicting speeds, signals collide and the system crashes. To prevent this, the motherboard relies on the system clock, a quartz crystal that vibrates at a specific frequency. It sends out millions of pulses a second, ensuring that data only moves when the beat drops. The clock is the internal metronome. By enforcing strict timing, it turns a potential electrical disaster into a synchronized symphony of logic. The CPU finishes its calculation. The result travels back across the bus system and is routed to an output device. Physical output used to be an analog process. You had to wait for a dot matrix printer to hammer ink into reams of paper just to see the results of a program. Today, those pulses hit the pixels on your display or the coils in your speakers. The unorganized binary data that entered the system has finally been contextualized. At the exact moment you read the screen or hear the audio, data becomes information. A computer is a profound ecosystem where software logic, hardware engineering, and human psychology collaborate to turn the raw signals of our world into knowledge.